Welcome back. So, in this lecture, I will introduce you to the process of risk assessment. The overview of this lecture is as follows. We will discuss on why we need risk assessment and its avoidance using NCRIA TR R15306201. This is the standard. We will discuss the prerequisite for risk assessment of injury severity, exposure, avoidance factors. We will discuss on determining the risk level using SEA analysis, sample risk assessment data template and risk reduction measures. So, why risk assessment? First of all, why is it so important to have risk assessment for collaborative robot environment? First of all, collaborative robots, they work alongside humans. So, ensuring their safe interaction is in paramount, because you see robots and humans, they have overlapping workspace and they are in very close collaboration. They touch each other, they handle each other, right? So, it can hit the human anytime. So, in that case, you have to assess the spaces, you have to assess the surroundings, you have to access the power and force limiting thing, everything that is related to safe interaction. So, this safety is very important. Next comes is collision avoidance. The cobot move within shared workspace. So, that is the reason collision is quite probable. So, how much force a robot can put on to the human, right? How much force a human required to handle a robot. So, all these parameters we need to study. So, risk assessment allows us accessing those parameters and parameters for collision avoidance. So, that is what is to be assessed as well. Task complexity. As the task goes complex, you need more and more interaction things, like for a pallet pickup, let's say it has to pick up from a place, it place it down somewhere. So, it is two tasks which are there, picking up and placing it. Let us say if the task goes little more complex, let us say you have to insert a pallet inside a hole. So, in that case it picks up, it inserts it, right, it releases it and it picks up the other one or it places it somewhere. So, the task becomes little more complex. So, as the task goes more and more complex, interaction between human and the robot becomes more and more. So, risk assessment help us to determine appropriate safety protocols which are to be followed for each subtask, right. So, task complexity is very important, right. Cobot design risk assessment helps us to determine the cobot, right, which cobot we have to put it in use, how a particular cobot is to be designed. This is at both the ends. One is for the manufacturer, other one is for the integrator or maybe the developer or researcher, right. It helps us to determine the reach, payload capacity, joint flexibility or end effector compliance that you are looking for a particular application, right. So, that is why risk assessment helps us to determine each of these parameters which are very important. So, next comes is human cobot interaction or human robot interaction. In this case it is a cobot. So, considering factors like proximity, how close a human is going to be in the workspace of the robot, what forces, interaction forces that will coexist between the robot and human, speed during the collaborative task, how much speed this task is going to be executed. It can be quasi static, sometimes the contact could be a transient contact, so you never know. So, is there any probability of having such transient contacts as well? So, all those things we need to determine beforehand. So, risk assessment, I tell you, it is done twice at least, once during the implementation of any task that is assigned to the robot, and second one if at all there is any incident that has happened. So, this also risk assessment helps us to evaluate the protocols which have been violated, right. So, that is why it is very important. It helps us to decide on the safety measures and the training that we need to provide to the operator, right. Area analysis, optimization of the layout, lighting that should exist, because you see human need sufficient light in order to see the things around, right. A robot may use some other kind of sensors also, but human, they rely mostly on vision, right. So, any obstruction ensures safe operation. So, any obstructions is to be analyzed. So, whole of this work area need to be analyzed. End of arm tooling, commonly known as EOAT. Accessing the attached tool ensures the safety of humans around. So, end of arm tool, it may have some surfaces to hold the object which it is handling, right. So, if that surface goes wrong, so your object may fly away while it is transporting from one place to other. So, if at all you haven't done any risk assessment or any estimation of those surfaces, right, textures and all, how do you know? So, that is why end of arm tooling, whether that arm has already finished its life. So, you never know. So, those things needs to be assessed also. Continuous improvement. See, risk assessment helps us to do continuous improvement. It is not at the time of implementation of any task which is given to the robot, or at the time of incident it is done. It is a continuous improvement task. Sometimes it is done intermediate also, like in case of plant maintenance system or some kind of regular interval, they do some kind of checks. So, that is why it is very, very important. You see, continuous improvement to maintain the balance between the productivity as well as safety. So, both should be in the paramount, right. So, you cannot lose productivity in the name of risk assessment or something. If it is necessary, we will do it. If it is not, we can simply skip it for the next time, okay. Or there may be some preliminary checks which are done before every start the robot is done. So, there may be a starting procedure, a stopping procedure that goes every day. It is a continuous task, but sometimes it is done at the starting when the task is assigned to the robot, not every day, and few tasks which are done at the end, maybe when you are decommissioning the robot for a different task, you are assigning it maybe, okay, or maybe after some kind of incident that has happened. So, yes, continuous improvement, it is very, very required, and for the compliance to various safeties, right. So, you have learnt about various ISO standards which applies to the cobots. So, yes, basically compliance to standards like ISO 10218, that is especially for cobots, that is very, very important here. It ensures consistent in safety practices across different scenarios. So, we will look at ISO 10218 very much in detail, because that is the one which goes actually in doing the risk assessment task, apart from the ones that we have discussed in the previous lecture. What is risk assessment and avoidance? It is normally done using various standards, various similar standards which exist across different nations. It is adoption of ISO 10218 1 and 2 to 111. Again 2011 is the year when it came in, and then it is revised after every 5 years or maybe in between also, that depends. Okay, so these standards are updated after every cyclic review process, right. So, you should not just take in any standard as such, right. So, yes, risk assessment standard, that is ISO 10218, is adapted across various nations internationally. In India also we follow this one, the base guidelines which are there in ISO 10218 1 and 2. 1 is for manufacturer, 2 is for integrator. In Canada it has some other name, right. So, same adaptation has gone in there also. In China it is there, Denmark, Europe, Germany, Japan, South Korea, Taiwan, UK, Brazil and US, right. So, basically I will discuss today ANSI RIA release 1506, that is what it has. So many other things apart from hazard identification and risk assessment. It also has chapters on design requirements and protective measures for the cobots, actuating controls, what goes in actuating, what all controls it should provide, if at all it is a safety related control system performance. Apart from a standard control system, it has a dedicated safety related control functions also. So, what should be the isolating workspace maybe, or it can be Cartesian workspace which can be isolated. There may be joint limits in the software end. So, those things. Safety related control system performance also is evaluated here. Okay, robot stopping functions, in what all scenario robot should stop, what functions this robot manufacturer should offer to any programmer, speed controls, operating modes and pendant controls, what all emergencies which should be there on the teach pendant of the robot, that is primarily used to teach a robot, maybe emergency stop it is talking about, or maybe 3 position switches which are there at the back of your teach pendant, sometimes in the front also, like control of simultaneous system, how many number of IOs or how many number of simultaneous, let us say if it is a turntable, it is a linear rail, it may be a conveyor. So, how many such simultaneous systems that can go along the cobot operation, that is also discussed in this. Collaborative operations requirement, the pressure limits, force limits, so those things. Singularity protection, this is very very important. What would happen in case robot goes to a singularity? In case of regular programming, you always take care while programming only, but in case of cobot, even due to some external forces, robot may enter into singularity zone. So, if at all it goes into singularity, what should be the behavior of your robot? So, those things are explicitly discussed in case of cobots. Axis limiting and movement without drive power. So, if at all there is any power failure, what would happen to the joints? Whether the brakes will be applied or robot goes safely to the home position using its backup power or something. So, those things are discussed here. Provisions for lifting, electrical connections, what safeties, what should be the standard of wiring that is used. So, all those things are discussed here. So, we will focus on hazard identification and risk assessment only next. Okay. So, let us begin with that. So, prerequisite for risk assessment goes on like this. So, the first thing which before risk assessment we need to create a team, right. So, team may comprise of operators who is actually operating the robot, technicians who maintains it, who programs it, right, managers on the shop floor. There may be multiple number of systems which are there, manager may take care of all those. So, he may be involved, any specialist if he is there, maybe a cobot specialist, an insurance guy, like stakeholders, all the stakeholders who are responsible to run and operate this cobots may be the part of the team. So, while accessing the risk of a system, not just a cobot, team may be formed that has all these. Okay. They identify the cobot, integrated system operating process. You need to identify the process where things can go wrong, right. So, those things are to be identified first. In case of cobot, it is cobot and there are many other integrated systems. It may be a turntable, it may be a linear rail or a conveyor. So, whole of the systems are to be identified for which risk is to be assessed. Next, collect information, like what are the limits here, okay, what are the safety locks. In case of industrial robots, it can be a door, if it is opened, robot will not start, right. So, if it is emergency stop switch pressed somewhere, so it need not to start, right. So, there are many other such interlocks, mechanical and electrical, which does not allow robot to operate until unless those interlocks are freed upon. Okay, there are many other safeties. What is the life cycle? Let us say if it is a tool which is at the end, life cycle of tool is to be checked. Like design of the cobot, which particular design, is it suitable for this particular application or not? Specifications, what is the repeatability, how much is the compliance that is possible with this kind of setup, right? Wiring, any safety bypass, this normally should not be done. It is never to be done, but if at all post assessment if it is found, this is to be identified as well, and it is to be marked. Okay. Energy sources, where from the energy is coming, is there any emergency source exists or not, accidents or maintenance history. The history of cobot is to be studied before we do any assessment on that. If any major overhaul and any of the access was done, is to be taken care of. Training, if it is training is provided to the operator, personal protective equipment, what all equipments are required. So all those things needs to be covered here. Procedures for robot installation, maintenance and usage, it should be clearly followed while doing the installation. Before doing any maintenance, one should read out that, and they should follow the proper maintenance procedures, and also while it is in operation. Any manufacturer's recommendation for these tasks as well. For maintenance, special or standard tools which should be used to do maintenance, spares, proper spares should be there, not a third party spares are not prescribed. Any operating procedure to do such maintenance, any local or industry standard procedures should also be considered, not just the manufacturer's recommendation. Every industry scenario may be different, so depending on that, those precautions should also be noted down. Identifying the hazardous area, like any edges, sharp surfaces, rough surfaces kind of surfaces, end of arm tooling part. Okay. Follow the subtask hazard approach. Every subtask you have to split whole of the task which is performed by the robot, right. Whole of that task is to be split into multiple small subtasks. Each subtask can have their own hazard. So you have to split them all and then identify the hazardous area before you do that, right. Assumptions, there are few warnings on that. Machine is practically safe, this is an assumption and this is 100% wrong. No fencing is required, so it is never a case for a cobot. There may be, it depends on application to application. Robot may require fencing as well, even if it is a cobot working on pressure force limiting. So this is again, it is an assumption, it is 100% limited, so nothing will happen to an operator. So these are few assumptions. All safeguards are in place, so you have to remove all the safeguards while you do any assessment. You have to think as if it is not there. Anything can go wrong, right? Even the safeguards can go wrong. So all the evaluations should be done with the safeguards not in place. So you cannot assume that it is there, so nothing is going to happen. Zero risk is a myth. There is nothing called zero risk, only tolerable risk is achieved. Okay. So machine is never practically safe. You got it? So these are some of the assumptions and it may or may not to be considered. So identify the risk level and the required risk for risk reduction. So what all things that should be done in order to make it a safe robot, right? So you have to identify all the risk levels and the appropriate risk reduction procedures, right? First, shut down. Post accident, you have to shut down, sign it off. People are doing some inspection, you have to flag it off. Even while maintenance, you have to do this. Even while installing and doing the inspection post accident. So this is a regular procedure. You have to shut down and sign off before any operation which is done on a robot or even a cobot. Okay. So this is an industry best practice, but one can design their own process based on the best practices in the industry. So these are some of the prerequisites before we start. So how it is actually done? So as per NCRIA, this is standard table 1 that is there in the standard injury severity factor, as letter is there for this. So based on injury severity, it may be classified as serious, moderate or minor. So serious could be normally non-reversible. Okay, in this case, the person, the operator is likely not to return to the same job after recovery from the incident. It may be It may be result of any of these like fatality, limb amputation, long-term disability, chronic illness or something like that. In case of more moderate, it is a reversible thing. The operator comes back to the job after recovery, and it is maybe a broken bone or laceration that has happened, like short hospitalization, short disability, those kind of things, right? Or even sometimes tip amputation, not the thumb, is considered as moderate. Minor is first aid. With the first aid, normally he comes back to the job. It may result in bruising, small cuts, no loss of time, multiple day, and does not require attention by a medical doctor. So, based on injury severity, it may be classified as S3, that is serious, moderate S2, minor S1, right. Next is exposure factor. Exposure factor, how much exposed you are. Exposure factor, it may be high, it may be low. So, in any of the following are applicable, it is rated as high, typically more than once per hour. If person and robot is interacting more than once per hour, frequent or multiple short time interaction, short duration interaction, duration situations that could lead to task creep or do not include this do not include a teaching process. Teaching people get involved to a longer duration. So, all these are considered as high exposure, right. A low exposure could be either of these, typically less than once per day or a shift, right. Occasional short duration is okay. So, this is considered as low exposure, right. Next is avoidance factor. Can it be avoided, right? Avoidance factor. So, not possible, not likely, and likely to be avoided. So, these are a few points in that, like insufficient clearance to move out, right. So, an accident cannot be avoided, right. If at all things happen, it does happen, you have no way to go out. Safety related reduced speed control is not used. It is not used. Robot system layout causes the operator to be trapped with escape route towards the hazard only. He cannot escape. Safeguarding is not expected to offer protection from the process hazard. Example, explosion hazard. Right. So, in any of these, it is considered as avoidance is not possible, and this is dangerous, you see. Next one is not likely, insufficient clearance to move out, safety related, reduced speed is used. Over here it was not used, over here it is used. Obstructed path to move to safe area, path is there but it is obstructed. Hazard is moving faster than the reduced speed, and this is also defined 250 mm per second. Inadequate warning and reaction time, might not perceive the hazard exists. So, end user may not see that hazard is there, right. So, that could be the case. So, in all these cases it is not likely, and the last one is very likely that it can be avoided. So, sufficient clearance to move out is there, hazard is incapable of moving greater than reduced speed 250 mm per second, adequate warning and time is there, positioned in a safe location away from the hazard. So, in this case it is likely to be avoided. So, based on SEA analysis, S for injury severity, E for exposure and A for avoidance, right. So, you classify the kind of risk level. So, this is the risk level classification, whether it is very high or negligible depending on this. Okay. So, based on the above S, E and A category, see if it is S1 and E0, E0 is totally prevented, it directly goes to the negligible. But if it is E1 and A1, it is likely, so again it is negligible. So, accordingly, so if it is S2 and if it is E0, it is still prevented and it goes to low. But if it goes to S2 moderate and E2 high, and A2 or A3 not likely and possible, it goes to high. You see, so depending on different combinations, it reaches to negligible or very high risk factor. Okay, so very high risk level, right? So depending on the various combinations of severity, exposure and avoidance, risk level is determined. That is table 2 of this standard, right? So now how do we do a risk assessment for a given job, right? So this is a sample table that I have shown here. It is also there in the standard. So sequence number for the task description comes here. For example, I will tell you. So let us say this task could be a general housekeeping task to see. Okay, the person, this is a housekeeping task. Okay, the hazard could be he may fall from a height, he may be climbing up a ladder and he may fall. In that case, the severity may be S2, E1 may be the exposure level, A2 could be the avoidance level. So accordingly, it may come up to S2, E1 and A2. Let us go back and see S2, E1 and A2. So you see risk level is high, that is shown here. So it comes in a high risk level category. So then again the solution is recommended by the risk assessor. Okay, he may say, okay, use a platform or a taller ladder to do this. So that is the recommended solution which is given, and then once it is done, solution is implemented, again you do the risk assessment. In this case it may have some better case. So in this case it may be E2, it has come down from E1 to E2, avoidance has become A1, it is totally avoidable, and severity has also reduced from S2 to S1, and then new risk category goes to S1, E2 and A1. So you see now S1, E2 and you see it is A1, but if it is E2 it is low category. Okay, so it goes to low, you see. So then you see for every such task you create such table, and there are some recommendations and solutions which are recommended. After implementation you go back and do the validation. Okay, that makes the table complete. Okay, once this is formed, then you do the risk reduction measures. Some measures could be like this. Okay, based on the risk level category, one or in combination of the following are required as means to reduce the risk to acceptable levels. The validation, as you have seen, is performed after the recommended solution is implemented. So it may include elimination or substitution of the hazard, that gives you a new severity level. Frequency may be reduced, it may become avoidable now. Okay, engineering controls like interlocks can be put, safety curtains can be put, limit switches, barriers can be put, and engineering controls can be of two kinds. It can be passive, it can be active. Passive controls could be limiting the moving masses, inertia. You are reducing the inertia of the system, maybe the object, maybe the robot, right, or accessories. Rounded edges, soft surfaces, you try to use them. Natural compliance, how much should be the natural compliance of the system. Padding, if it is possible, you fit it. Active compliance or active engineering controls are limiting the forces and torques. That is done by the robot programming, that is normally present in any cobot. Velocity or momentum reduction. Virtual limits, even when there are physical limits, there may be some virtual limits at the software end that further limits it to certain levels. Okay, joint or end effector compliance, how much is required for this particular task, so they can be put. So active and passive, there are two types of engineering controls. Next comes is administrative control, that is safety awareness. You have to make the people aware, the operator aware of these things by putting light signals, signs, posters, beepers, computer warnings. If at all your robot is controlled by some kind of HMI, human machine interface, it can pop up with an error showing that this operation would cause this errors, or this warnings they exist for this particular task. So that it is actually warning the operator first. So that could be there as well. Next comes is proper training and safeties, inspection, operating, maintenance procedures is to be followed, right? And the final one is personal protective equipment. Proper gloves should be worn. If required, eye goggles are to be used. So those PPE gadgets should be in place. So you see the first point, 2 points, this and this dealt mostly with engineering, while the others are administrative procedures. So they are dealt in a different way, right? So this is how risks can be reduced. So ultimately you follow the complete procedure, and finally risk is assessed, and finally it is reduced. Okay. So that's all for this lecture. In the next lecture, we'll see how the force control that goes as a primary technology behind any cobots, how it has evolved, technology transition. We'll see how the technology has transitioned over the years and what it is now. Fundamental technological difference between industrial robot and a cobot, that we'll see. Cobot hardware changes, what was done in terms of its arm, its controller, and the overall system. So all these we will be discussing in the next class. So that's all for this lecture. Thanks a lot.